Hi, this is Victoria Kabat, and this is my Lab 3 magnetic field of a bar magnet. So as an introduction, the purpose of this lab was to learn about magnetic dipoles and how distance affects them, and then we used a bar magnet to model the magnetic field variance on axis and off axis, and then Biot-Savart law to calculate B fields at these locations. So some results, we found that distance dependence n was negative 2.8723, the magnetic moment mu was 5.233, and magnetic field at 45 degrees experimentally was 2.5533 e to the negative 5, 3.5 e to the negative 5, and computationally it was 1.1448 e to the negative 5 and 3.43439 e to the negative 5. So some physics principles involved. The Biot-Savart law for a single charge was used to derive a B field equation for a magnetic dipole and also the B field of a bar magnet's magnitude. And then we also use Earth's magnetic field to adjust for the magnetic north with the bar magnet. And then distance effects on the magnetic field. The further away from a source, the smaller magnetic field. The closer to a source, the larger. So process began by compensating for magnetic north. So we used a testimeter app to place the magnet where B sub x was closest to 0. And then we added a ruler to show the orientation from east to west of the magnet. So using GeoMag and this location, we found that B net was 49. So finding the magnometer chip was the next step of this experiment. So I moved my phone perpendicular to the ruler that we had placed until X max and Y min were found. And then I moved my phone perpendicular to the tape after I rotated it until Y max and X min were found. And I found that my magnometer chip was in the top right direction of my phone when it is laid on its side. So some Excel data, the plot shown to the right is the linear plot that I found using my data. So my equation was y equals negative 2.8273x minus 13.77. And then to the left, I have my on-axis data at different distances. And then at the bottom, I have my off-axis data at different distances of d perp. So some experimental observations: when the magnometer is close to the bar magnet, the magnetic field in the x direction is a lot higher versus when it is far from the magnet. The magnetic field is approximately 0 in the x direction. So some experimental calculations, I found k, n, and mu. So k I found by doing e to the ln of k from the linear plot, that is 13.77, and that gives a k of 1.0466 times 10 to the negative 6, and then n is just the slope of the linear plot, which is negative 2.8723, and then I found mu by solving k for pi divided by 2 mu naught, which I found to be 5.233. So some computational code that I have for my method and model, I defined the constants in B field function first, which is shown to the top right, and then I made arrows for the on-axis, off-axis, and 45-degree B field, which are shown to the left. So my computational results, when you run my code, the model displays the orange arrows for the B field on axis, the cyan arrows for the B field perpendicular, and the magenta arrows for the B field at 45 degrees, which is equal to 1.1448 e to the negative 5 and 3.43439 e to the negative 5. So some result summary, I found that the B field changes depending on the observation location you're using. So the three calculations that this lab were centered around were the distance dependence, which was negative 2.8723, and the magnetic moment 5.233, and the magnetic field at 45 degrees experimentally it was the same numbers, 2.5533 e to the negative 5 and 3.5 e to the negative 5, and computationally it was 1.1448 e to the negative 5 and 3.439 e to the negative 5, and then I found percent differences for n with a theoretical value of negative 3 to be 4.257%, and the percent difference of the magnitude of the B fields at 45 degrees computationally and experimentally were 19.67%. So in conclusion, if we didn't orient depending on magnetic north, there would be inaccurate readings for the Tesla meter just because you're not zeroing it and Earth's magnetic field would be influencing it. And if you stuck two identical bar magnets together and ran it again, the results would be a lot higher just because the two bar magnets are increasing the field. But it's not necessarily double because it's not exactly linear. So if you have any questions, please let me know, and thank you for listening. Bye-bye.